Hello. Today we are going to discuss Ehrenfest's theorem. The Ehrenfest theorem states that the Schrodinger equation leads to classical laws of motion on the average. Classical laws of motion means Newton's laws of motion. I can say in other words, the average motion of a packet agree with the motion of the corresponding classical particles. So we know the Newton's law. We may written like this: dr divided by dt uh, p divided by m. I mean, this is momentum, right? P equal to mv, right? So this is Newton's law, which means rate of change of momentum is nothing but Newton's second law. In place of force, I used here the force can be expressed in terms of potential energy. So these are the corresponding components of um, these values. Okay, momentum and Newton's law corresponding component x component, y component, and z component. So we know the equation of motion h cross dx divided by dt square bracket x comma Hamiltonian. Just put the Hamiltonian value here. So once you use Hamiltonian here, Hamiltonian is the p square divided by 2m plus v. So after using Hamiltonian in place of h, I got this equation. Then just split this equation according to the fundamental brackets relations. So in case if you want to use this one, you're going to split like this. So we know commutation brackets of position and potential energy is equal to 0, and this term is going to 0. We have only first term x comma p square. 2m is there here, okay, outside the bracket I written here 2m. So then again I'm going to split this equation, um, uh, x px p x plus p x comma px square bracket of x comma commutation relations of x comma p, component x component is the I h cross. That information I already used, and second term is this px, this component I h cross. So total value here 1 divided by 2m IH cross 2 IH cross px. So let's go and cancel these two information. What we'll get here, the final equation we got, um, dx divided by dt. So we got px divided by m. This is one component. So like that, we'll get all the components. Dy by dt equal to py divided by m, dz divided by dt, dz divided by dt equal to pz divided by m. So you will get all these informations. You can follow the same procedure, same steps. You'll get these three components values. Therefore, one equation we already proved this one. Dr divided by dt is nothing but p divided by m. P divided by m. Here r is represented x plus y plus z. I mean ix plus jy plus kz. So we prove this information. First step. Second step is we need to take this equation of motion. IH cross dpx divided by dt equal to px comma h. Now you take this equation of motion, then go for basic steps. dpx divided by dt equal to 1 divided by ih cross px. In place of Hamiltonian, just use Hamiltonian value, x component only. Just V is the potential energy of a system. Then you need to simplify this one. IH cross Px comma Px square divided by 2m and plus IH cross Px comma V is the potential energy of system. So we know Px and Px square equal to 0 from computation bracket. Px come Px square equal to 0. Then remaining term is only one is 1 divided by IH cross Px component comma potential energy of the system. Okay. So this one is computation bracket, right? We know this relation computation brackets AB minus BA. I'm going to write like that 1 divided by IH cross PXV minus VPX. So just use the operator terms, momentum operator term minus IH cross dou by dou x to V minus into minus plus V IH cross dou by dou x, right? So dou by dou x, this term is 0. Then we have this one is going to cancel. Minus dou V divided by dou x. This term is 0, right? Differentiation of 1 is nothing but 0. So we got dp divided by dt x component. Similarly, if you want to follow all the steps, same steps, repeat the same step y component, z component, you will get the y component and z component. So in general, we can written this Ehrenfest's theorem dp divided by dt equal to grade v. Okay, so this is the Ehrenfest's theorem. So this equation gives the information the average motion of wave packet agree with the motion of the corresponding classical particles. This is the Ehrenfest's theorem. Thank you. We will meet again.